Hello everyone, my name is Sagarika. Today I will present the architecture and deployment of a real-time EV dashboard and advanced driver assistance system. Our roadmap today covers 12 distinct areas. We will begin with the ARM core hardware layer, walk through the toolchain and analyze fundamental on-chip peripheral. Then we will dive into our custom EV control, predictive ADAS, and fault handling software modules before evaluating our real-time telemetry link. ARM processor. The system core is built on the ARM architecture as a reduced instruction set computing or RISC pipeline. It executes instruction efficiently using simpler, highly optimized operations. This architecture provides the high processing throughput, minimal power draw, and low silicon footprint. ARM processor family. ARM categorizes its processor onto three application profiles. Cortex A handles application-heavy systems like infotainment screen. Cortex R supports safety-critical hard real-time systems such as braking module. For Cortex M series is highly optimized for power-sensitive, low-cost, and uh, requiring deterministic execution. ARM Cortex M series and Cortex M3 core. Within the microcontroller space, the Cortex-M family balances processing power with the ease of development, while the M0 core targets ultra-low power entry devices. The Cortex-M3 core handles interrupt handling. Our project runs on the Cortex-M3 based STM32F103C8 T6 blueprint. For advanced applications, the Cortex M4 adds a dedicated digital signal processing instruction set and an optional floating point unit for motor control loops. The high-end Cortex M7 introduces a dual-issue execution pipeline and a cache memory to handle computation loads like image processing and advanced ADAS units. Overview of a project. The core objective of this introduction are to design and implement a real-time simulation and ADAS model layer using the STM32 call library. The engineering focus was to interface user arrays, build real-time control logic, and stream parameters cleanly to an external graphical interface. Development environment and workflow. Our tools use STM32MX peripheral-based register initialization and pin mapping. Firmware was written in embedded C using STM32 Cube IDE. Hardware and the loop behavior was verified in the Pixim Lab emulator, and the initial pipeline integrity was confirmed through a non-blocking LED blinking test. STM32 fundamentals and peripherals used. The Blueprint microcontroller utilizes on-chip peripherals to connect software loops to hardware signal. We mapped GPIO for digital triggers and ADC for pedal voltage sampling, a UART link for external communication, and hardware timer to handle event scheduling and PWM execution. Electrical vehicle and core architecture. An electric vehicle replaces the conventional internal combustion engine with the electric motor driven by a high voltage battery power. Propulsion control is split between a motor controller managing torque loop and a battery management system monitoring battery thermal limits and state of charge. Advanced Assistance System ADAS comprises electronic safety system designed to actively monitor a vehicle's surrounding, while real-world implementation combines cameras, radar. This project deploys a three-axis acoustic array HCSR04 ultrasonic sensor to achieve real-time obstacle boundary tracking. EV powertrain and ADAS system synergy. In this domain architecture, both modules run simultaneously. The EV layer tracks internal traction variable while the ADAS layer maps external environmental grids. Both modules merge their data into a single UR telemetry stream, presenting a unified view of vehicle health and activity safety states. GPIO, General Purpose Input Output. GPIO pins form the fundamental digital link between our code and the outside world. Each pin can be dynamically mapped as an input to catch sensor transition or as an output to generate trigger signals, enabling fast, low overhead digital device control. ADC mechanics to read physical continuous voltage, reconfigure the STM32's on-chip 12-bit ADC. The 12-bit resolution translate analog pedal position into precise digital integer values from 0 to 4095, giving our powertrain control algorithm highly accurate driver intent data. UART serial communication data telemetry relies on the universal asynchronous receiver transmitter protocol. Because UART is asynchronous, it receives the hardware overhead of the shared clock line. Configured at a baud rate of 1,15,200, it streams packaged metrics directly put off the microcontroller PX pin to the dashboard interface. HCSR 0 ultrasonic sensor. For spatial mapping, we deploy this ultrasonic sensor when prompted by a 10 microsecond high pulse on its trigger pin. It fires an acoustic wave array at 40 kHz. The sensor pulls its echo line high for the exact duration of the sound waves. Round trip time of flight accurate within a 2 to 400 centimeter range. Hardware timer independent execution. Hardware timers are specialized on-chip peripherals that count clock ticks at a prescaled frequency completely independent of the CPU. This independent operation allows us to measure precise execution steps, create deterministic event timings without using locking software rules. Event driven interrupt processing. Continuous register polling based fighter processor cycles. Interrupt resolves this by shifting the system to an event driven model. When an interrupt triggers, the CPU pauses the main thread. Context switches to the designated interrupt service routine to update system flag and immediately resume normal operation. Role of timers in interrupts. By pairing hardware timers with the interrupt controller, we generate precise periodic interrupts. When the counter matches the target value in the auto reload register, it overflows and triggers an interrupt. This eliminates the need for the software delays, ensuring accurate intervals for sensor sampling and control. Project overview. EV ADAS system description. Bringing these fundamentals together, the EV ADAS architecture treats the STM32 mobile as a centralized vehicle domain controller. The firmware handles analog driver demands, processes multi-axis acoustic spatial updates, runs predictive evaluation loops, and manages serial data and packaging. Core system objectives. Our system execution meets five primary objectives. It tracks internal vehicle powertrain models, estimates dynamic physical states, processes obstacle boundaries across three spatial arrangements, executes predictive safety routines, and pipes telemetry out to a dashboard display. EV control module dynamics. The EV control module automatically handles the vehicle's driving characteristics running inside a strict 10 millisecond window. It samples throttle and brake voltages continuously, calculates torque, instant power consumption, battery depletion, motor thermal climb, and remaining range. ADAS module safety logic. The ADAS module manages environment scanning through front, left, and right sensor. The algorithm provides forward collision warning, blind spot detection, and overspeed alerts. By factoring vehicle speed into obstacle distance checks, it calculates a predictive time to impact metrics rather than relying on basic static distances. Real-time processing architecture. Real-time execution requires strict predictability. The firmware uses a timer-driven architecture where hardware timers trigger interrupts to update execution flag. Complex calculations are kept out of interrupt service routine. Instead, the main thread pulls these flags to run task cooperatively. The 10 millisecond high priority control loop. The system splits execution into multi-rate loops. The 10 millisecond driven by timer 1 handles high priority traction tasks every 10 milliseconds. The processor checks pedal register, calculates vehicle acceleration, scales battery depletion based on drive modes, and updates operational states. The 100 millisecond low priority sensor loop. Environment calculation do not require 10 millisecond refresh rate. That 100 millisecond loop driven by a timer 3 handles low priority scanning tasks. Every 100 millisecond, it triggers the 3 ultrasonic field. The processor spatial grid paths and evaluates predictive safety alarms, reducing overall safety loops. Next, we have is fault mitigation system strategy. Dictates clear failure mitigation routine. When a system metric crosses a safety limit, the firmware sets a flag and switches to fault mode. The motor output is disabled instantly by dropping the PWM duty cycle to zero, forcing powertrain isolation until the conditions are cleared. Then we have system fault matrix table. The fault matrix maps specific system failure to an 8-bit register. It includes flags, motor, over temperature, low battery SOC, collision emergency. The state machine handles compound fault up to 0x07, cutting off the power chain when a fault flag is tripped. Data communication and dashboard. After each processing cycle, the latest parameters are packaged into a structured data packet and sent via UART. The data flows sequentially. Data is sampled from sensor, evaluated by the control module, formatted into a data frame, and pushed onto the serial line. Python GUI serial data ingestion. On the host PC, our Python applicable uses the PySerial library to handle incoming data. The script monitors the serial port, captures incoming telemetry packets, verifies data integrity, and gives the enable to update the user dashboard. Dashboard visualization engine. The Python application acts as a real-time cable dashboard. It runs a run-blocking display loop that maps incoming telemetry data onto digital user gauges, showing active metrics for vehicle speed, pedal position, battery state of charge, and motor health. The interface also tracks advanced system parameters. It displays instant motor power, active drive modes, and numerical distance grids for all three ultrasonic sensors, and active color coded safety indicator for forward collision warning and blind spot detection. In summary, our UR telemetry link ensures low latency communication with minimal CPU overhead. This project successfully demonstrates how fundamental embedded protocols, hardware timing controls, and predictive software combines to create a modern, dependable automotive system. Now we will have a look at a simulation or demo of the project. Here is the code we have written for our ADAS project. Here is our main C file in which we have written our main code. Then we have our modules, that is, we have created header files and source files. Our modules include ADAS, common, EV control, fault, main, UART, shell, and ultrasonic.h. We have performed our simulation using Pixel Map and the spare parts window. that is evdash.pin. So here is the reading we are getting. Our buzzer was, our yellow LED was going because our torque was 0.36 seconds and it was correctly shown as fault 04. Then we have our front left right distance printed. Then we were getting fault because of we had distance less than 33 centimeter. Then time to collision was 0.3 seconds at last, so the fault was 04 and LED was glowing. So similarly, we can change our potentiometer reading also. And here is our blueprint configuration. Here, if time to collision was 0.33 seconds, we were getting critical alarm warning. Similarly, we can change our potentiometer readings also. For example, we can put the brake pedal to zero and just increase our ultrasonic distance sensor also like this. And then we can again upload our binary file to get the updated values. So here is the spare parts window opening up. So we are getting speed as 20, state of charge as 99 per second, torque 0, temperature 34.1, acceleration and brake values. We are not getting fault as of now as time to collision 99.9 second and the distance are also greater than 3 centimeters, so no blind spot detected also. And here we can have our here also we don't have any alarm or something like that because time to collision is 99.9 seconds, which is absolutely fine. If we don't have any blind spot or something like that, and speed is 20 kilometers per hour, which is decreasing very slowly. So here is our overall simulation, our Python dashboard, our Pixel lab, and our STM32 Cube ID board part. Thank you.